Section 4.3 is titled Rules of Logarithms. It's titled that way because your book titled it that way. I don't actually like the word rules. I would much rather it say properties. So these are properties that are held by logarithms. The first one is an inverse property. We've actually seen this at play a little bit already. If we have log base a of a, but now it's raised to the power of x, it equals x. And that should make sense in some fashion from our scorpion tails, because if we drew this arrow around and we rewrote it, it would say a to the x equals, and it lands on the a to the x next to it, and we would say, well, yes, they're exactly the same. Of course, that's a property. That makes sense. The same is true for the second one. If we were to draw a scorpion tail, there's my base, and we were to rewrite it in exponential form, this would be log base a of x, and then it lands on all of this at the top, which says log base a of x. So what these properties are actually telling us in a very convenient form is that if I have log base 5 of 5 to the 3, these pieces at the beginning very much cancel each other out in terms of operational sense, and I'm simply left with the exponent 3. So that's a very convenient fact, and the same thing for the other one. So when I have, on this example below on part A, the common log of 10 to the y plus 1, the common log part here and the base 10 here are inverse operations, and they leave me with just the exponent y plus 1. That's what this property is telling me I can do. It's kind of like, you have probably seen the little trivia things that come out sometimes. They happen on social media now. Back in the day, before social media, they would come around on these emails, and my grandfather was one of these ones. He's 90 years old this year, but he had email when it first started being a thing. He was very cutting edge for an older person, and he would be very excited when it would say something like, take the year, add this number, and then multiply by this number, and then do this to it, and then do that to it, and notice what happened, and this is the only year it's ever going to work forever. And he would be like, whoa, very exciting. And whatever happened always, because he would always send it to me because he knew I enjoyed math puzzles and things, and he would be like, why does this work? And it was always because they were doing this. They were doing something where they were like saying, multiply by 3, and later in some fashion they were dividing by 3. Right? You did one operation and then you did its inverse operation somewhere else. That's all that's happening here. These are inverse operations, and that's why they cancel one another out. The same thing happens on part B, right? So we see the base 7 in exponential form, and then we see the log base 7 in log form. Those are inverse operations, hence they cancel each other out, leaving you with 999. So it's a beautiful inverse property. The next 3 all have relationship back to our exponential properties. So do you remember in our exponential properties when you had the same base multiplied with different exponents, we add the exponents? And we had the same base and they were divided, we subtracted the exponents. Do you guys remember that? Things that looked like a to the m, a to the n is a to the m plus n. Y'all remember these, right? The properties of exponents. So the next 3 properties for logs very much look like those same properties from exponential equations, and that should make sense because they're inverse operations. So the first one says that if you have log base a of m times n, you can separate it into 2 logs where you're taking log base a of m and log base a of n and you're adding them. Okay, so that's very much like the one that says a to the m, a to the n is a to the m plus n, right? Multiplication in one piece, and piece of it looks like multiplication, the other piece it looks like addition. The quotient one, again, I see log base a of m divided by n, and so I end up with subtraction. Also looks an awful lot like the a to the m over a to the n, and I end up with subtraction, right? That's its counterpiece with exponentials. The last one is not a reflection back into exponentials, but it's actually a building upon itself. It says that if I have log base a of m to the power of x, that I can bring this power of x in front as a coefficient, right? That's what it's saying. But let me just do a real simple example of why that should make sense based on the property that is number 2 up here. If you had log base a of m squared, I'm just going to use m squared is the same thing as m times m. And then property number 2 says that I can do log base a of m plus log base a of m. Well, that's just 2 log base a of m's. And so you see that 2 that was the exponent coming in front. So it's just a property of repeated addition, right? It becomes multiplication. That's really what's happening there. What these properties allow you to do is they allow you to take things that are in like a very condensed, compact log form and expand them out when that's helpful, or to take something that's in an expanded form and it allows you to condense them back together. And that's actually what we're going to be using them for. So let's actually do the combining them back together one for the first one. So we have this multiple logs written out, and we're wanting to sort of mush them back together into a single log expression. The single log expression shouldn't have any numbers in front of it, all right? And there shouldn't be multiple logs, obviously, with it when we're done. So the first thing to catch and to make sure of is, in fact, that we do have powers, or coefficients, excuse me, of 1 at the beginning, and these do, right? I don't have a number in front of either log. If I did, I'd want to be using property 3 to start with, pulling those coefficients and making them exponents. I don't have that here. So what I do have instead, I've checked that, is I have addition. So addition of logs means that I'm equivalently on the right-hand side of property number 2. So I can take something that's written out as addition and I can mush it back together and I make multiplication inside of the logs. So I take my log 3 and I write it simply one time. And then the interiors of the logs, what's inside of them, x minus 1 and x, get multiplied together. You can leave it written like this, or another version might be that you multiply the pieces together and it says x squared minus x. Either of those are fine. I've accomplished the directions. I have a single log expression with no coefficients in front. Part B, I have coefficients in front. And the reason that I mention the coefficients in front, even though it kind of feels like, well, but the directions didn't say anything about eliminating coefficients, is that properties 2 and 3 here only work when the coefficients are 1. Okay, I can't just have any random coefficient and have this work. The coefficients for properties 2 and 3 have to be 1, which means if I don't have coefficients of 1, which I don't on problem B here, I have to use property 3 to make it so that I do. So the first thing that I will have to do on problem B is I will have to take each of these coefficients and I will have to make them exponents on the insides of the log. So I have the natural log of 6 to the 1/3 minus the natural log of 2 to the 1/3. There's one other way I could do this problem I'll show you in a minute, just because the coefficients happen to be the same. Now this is subtraction, right? So the subtraction property is property number 2. It says if I have logs that are subtracted, what can I do? I can divide their insides. So this is not the log divided by the log. That is not what I have. I have a single log when I'm done, but it is a log of division. Okay, so the division is inside of the log. It's not division of 2 logs. The top is the 6 to the 1/3. The bottom is the 2 to the 1/3. Now, that can be simplified. Any thoughts on how I can simplify 6 to the 1/3 over 2 to the 1/3? Explain to me what you mean, David.
Well, they both have the same exponent.
Yes. So instead of thinking about it this way, I could think about it with a 2, yeah, this way. And I can actually do the 6 divided by the 2. You're exactly right. So because the exponent's the same, I have the ability to divide the 6 and the 2. This, in simplified form, would be either written as natural log of 3 to the 1/3, or if you prefer, you can write it as natural log of the cube root of 3. If I'd wanted to, instead of worrying about the coefficients, the coefficients becoming exponents at the beginning, I could have actually pulled the 1/3 out of both of them and dealt with these first. That's another option because they're the same. I just deal with the natural log of the 6 and the 2. I would divide the 6 by the 2. I would be in this position right here, and then I would move my 1/3 to the exponent position. That's another option. Okay, C is the most interesting. Are you ready? Definitely the most interesting, agreed. There's a lot going on C. These coefficients are not the same. It's really important to notice that. The last one they were, so I had a couple of different things. I said I could do this or I could do this. There's no could do's on this one. When the coefficients are different, they actually have to be dealt with first, for sure, to become coefficient or to become exponents instead of coefficients. So the first thing I will do is I will rewrite this as log base 2 plus log base x plus log base y to the 1/2 minus log base z to the 3rd. Is everybody good so far? Coefficients became exponents. Now here's the really cool thing. If you notice over here on the properties 1 and 2, it only tells you what to do when you have addition with 2 things or subtraction with 2 things, right? And that's really what it does. But you can do this for multiple items. You can have addition of 3 things, subtraction of 3 things. You just have to be a little bit careful in particular with the subtraction, because subtraction tells you that you do division. Multiplication, it doesn't matter the order of multiplication, but division, it matters, right? A over B is not the same as B over A. So when you're working with a problem that has multiple pieces, in particular what happens is that anything that's negative, the interior of that piece, namely in this case the z cubed, goes in the denominator. And anything that's positive, its interior goes in the numerator. So my 2, my x, and my y squared actually are all in the numerator. Not y squared, y to the 1/2. And my z, because it's the negative, is in the denominator. It's the subtracted a piece. So it's the only piece that's in the denominator. And this is the log. You can write log base 10 if you wish, but you can also just leave it as log of 2x y to the 1/2 over z cubed. Or if you don't like the 1/2, you can write it as log of 2x square root y over z cubed. There's no need to do that way, but it's possible the back of the book might do something like that if you looked at an odd one. Any questions on consolidation or collapsing of logs?
Can you just re-explain what goes on the top and bottom again?
Yeah, the ones that go on the top are the ones that have a positive sign in front of them. So on this one, that's the first 3. And the negatives are the ones that go on bottom. And it doesn't matter what order they occur in. Like it happened to be that my negative was at the end, but if the negative had been in the middle, it still would have been on the bottom, and any of the positives would be on the top, always. So we'll do some other examples later. Let's see if I had another one where you could actually just see it. No, I don't inside of this lesson, but you'll see some more on your homework for this. Okay, so this homework, 4.3, is not assigned for today. We will finish section 4.3 next time, and we'll pick up with expanding logarithms as opposed to condensing next time.